Yeah. So our next speaker for the morning is Rafael Oliveira, and he'll be telling us about scaling algorithms for polynomial identity testing. So, Rafael.
Okay. I'd like to thank all the organizers, all the three of them, for inviting me. It's a great workshop so far. Just working? Okay. Okay. And today I'll continue Ankit's talk. And I'll talk, this is joint work with Zewan Alenzu, Ankit, Anjali, and Avi Vigdersson. And so these are essentially, the broad title is Scaling Algorithms for Polynomial Identity Testing. And today we're going to see two scaling problems, okay, that Ankit already alluded to, which is matrix scaling, operator scaling. We're going to just revisit the definition of null cone, talk about some alternating minimization algorithms, and see a different algorithm to solve the orbit closure intersection, okay? And this algorithm requires this geodesic convexity that Ankit promised you that I would speak, so I'm hoping to speak about it in this 45 minutes, okay? So here's the first and most basic scaling problem that Ankit talked about in his talk, which is the matrix scaling or balancing problem, okay? So we say that a matrix A, a complex matrix A, is doubly balanced if the L2 norms of the rows and the columns are all equal, okay? So for example, you can look at this matrix, the L2 norms here square. Just take the L2 norm square of these rows, they're 5, and of the columns are 5. So this is a doubly balanced matrix, right? And the B is a scaling of A, as Ankit said, if you can multiply A on the left and on the right by these diagonals, like with x1, xn, and up to in, such that, you know, then the entries Bij become xi, aij, yj, right? And then B will be a scaling of A, okay? And we say that this scaling, that A has a doubly balanced scaling if there exists a scaling B of A such that B is doubly balanced. So for example, if I give you this matrix here, you can quickly check that this matrix is not doubly balanced, right? But I can multiply each row by 1 and multiply the columns this way, and I obtain the doubly balanced matrix over there. This is not doubly balanced, but it has a doubly balanced scaling, okay? And the problem that we're interested in is the following. I'll define, instead of giving you an exact doubly balanced scaling, I want to know if I can get as close to doubly balanced scaling as possible. And what is my measure of how close I'll be from being doubly balanced is this distance here. And this is an ugly expression. All I wanted to get out of it is that here, it just means, so Ri is the norm, the L2 norm of the row I, Cj is the L2 norm of the row J, and here all I'm saying is that for every row, the norm of the ith row is roughly the same, right? So here's roughly the same, and this is roughly the same, okay? So this is your distance. This tells you how far my matrix A is from being doubly balanced, right? If this is 0, all the rows have the same norm, and all the columns have the same norm, okay? Okay, so now our problem is the following. Well, we say that A has an approximate doubly balanced scaling if for every epsilon, positive epsilon, there is a scaling of A such that the distance of this scaling to doubly balanced is less than epsilon. And our questions are, well, I give a matrix A, when does this matrix have a doubly balanced scaling, and can we find it efficiently? Okay, and how is this related to PIT? Right, I mean, that's the third question. So, okay, let me give you some examples of why we need the approximate version and not the exact version. The first is a computational problem, right? Like sometimes I can have a matrix, this matrix A, that has an exact doubly balanced scaling, but the scaling is with irrational entries. So definitely I'm not going to be able to output this scaling for you, right? I cannot output irrational numbers. So this is a more computational issue, but there's a deeper issue which is an approximate issue, right? That, you know, Christian and Ankit alluded to, is the orbit versus orbit closure, right? Like here, for example, I take this matrix, it has, the 1-1 matrix is the doubly balanced scaling, right? But if I scale this matrix, I can never make the top right entry to be 0. So I can never get this 1, 1, 0, 0 here. But I can get very close to it, which means that there is a doubly balanced scaling in the orbit closure, but that there's no doubly balanced scaling in the orbit itself. Okay, so there's a more geometric reason for it. Okay, that's why we're interested in this approximate version. And now our problem is, given a complex matrix A, okay, this M is like n by n matrices, and a parameter epsilon, is there an epsilon scaling to doubly balanced? Okay, I give you the matrix, I give you a parameter epsilon. Okay, and if yes, let's find it. And here's an algorithm that was proposed by people in very different areas of engineering, statistics, and the algorithm is the following. Take your matrix A. If the norms of the rows are different, just make them all the same by multiplying each row. You normalize the rows to make all the norms to be the same. Okay? But then you may have messed up the columns of A. Well, no problem. Use the other scaling to normalize the columns of A. And then just keep doing this. And if at any point you get really close to doubly balanced, you output the scaling, otherwise you say, okay, there's scaling. Okay? Now, you may have three natural questions. One is, are we making progress at all? Right? And if we are, how do we know when to stop? For which k do we stop? Right? And the other question is there an epsilon 0 such that if I can scale to epsilon naught, then I can scale for any epsilon, right? Because this would solve the question of whether I have a doubly balanced in my closure or not, right? Just means that I have to scale to this close to doubly balanced. Okay? So, okay, let me give you two examples of this algorithm of how it would work. Right? So here's the first, I'll give you this matrix. Okay? And if I normalize the rows, the norm of the rows, I get this matrix. It's a bit ugly. If I normalize the columns, I get this other matrix. And right now you don't see any pattern. But now, let me tell you that if you keep scaling, one thing that you notice is that the norm of this matrix, the L2 norm of this matrix, okay, just sum all the entries square, is going to keep decreasing every time I'm trying to do this fix. And at some point, you're going to get something like this. Look, from here to here, you notice that these, the 1s becomes 2s and the 4 become 5s. This is becoming more negative. And at some point, you're going to get something like this. Okay? If you keep scaling, you're going to get epsilon, epsilon. So this is being driven to 0. Right? Now let me give you another example where this algorithm is going to run. And now instead of doing L2 norm, I'm just going to do L1 because the numbers get really ugly. So let's just think about L1 norm. So I have this matrix. Let's fix the norm of the rows. Then, okay, now all the rows sum to 1. Right? Now we messed up the columns, so we fix the columns. Now all the columns sum to 1. And then I do it again. Notice that the denominators keep increasing. Right? But the numerators of the center here, of these guys, they remain really big. So at some point, if you keep doing this enough times, you get very close to this doubly balanced scaling. Okay, so you can see that all the row norms and column norms are the same. Okay? And the question is, how can we distinguish between these two cases, when something is going to 0 all the way and something is going really close to doubly balanced? Right? And the other question is, are these the only cases? Either I drive something to 0 or I drive something to doubly balanced. And what does this have to do with algebraic complexity theory, right? So in the first example, notice that we have this huge block of zeros, right? Which is this Hall blocker, which Ankit showed is a condition about the graph not having a perfect matching, right? And in the second one, we do have a matching, so we don't have this huge block of zeros, right? Is this the only reason why this algorithm should have this different behavior? And why is that so, right? Okay, so before we finish talking about this algorithm and analyzing it and seeing how invariant theory is used, let's talk about a generalization of this, which Ankit talked about and Anurag talked about before, that solved the non-commutative PIT problem, right? And this is this generalization of this matrix scaling problem done by Gurvitz, which is he called quantum operator. Okay, a quantum operator is a map that maps matrices to matrices, okay, n by n matrices to n by n matrices. Okay, and is given by a tuple of matrices A1 up to AM, and the map takes X to the sum of AIX AI transpose, okay, or conjugate transpose. And the only thing I wanted to get out of this map is that it takes positive semi-definite matrices to positive semi-definite matrices, okay? And now the dual of this map is essentially the map that you get by just flipping where the conjugate transpose is, okay? There's the same dual in the Hilbert norm, so like if you know what it is, if you don't, you don't. Just take this definition. Now, I promised you I'll give you a scaling problem, right? What is the analog of scaling here? And what is the analog of doubly balanced? And by the way, just to give you a motivation of why Gurvitz defined this problem, okay, to try to solve PIT by scaling. Okay? His motivation to define this quantum operator in his paper is actually, can we solve PIT by scaling? Okay, that was his attempt. Now let's see what the operator balancing problem is. Right, the operator scaling problem. So we say that a quantum operator is doubly balanced if, when I apply T to the identity and the dual to the identity, I get both of them be identity. So this is the equivalent of the matrix having like, you know, row sums all equal and column sums are all equal. Okay? And the scaling of T now, remember, T is given full of matrices A. So let's just think of full of matrices A. So the scaling of T consists of two matrices, left and right, which are invertible matrices determinant 1. And that's the left-right action that Ankit talked about in his previous talk. Right? So the scaling here is I multiply all of the matrices at the same time on the left by L and on the right by R. Okay? And again, the generalization of this doubly balanced is exactly what you'd expect. Is how far is my Ti from being identity, and how far is my T star of I from being identity. That's all, is the same thing as the other sum. Okay? It's just the generalization of that sum. You don't need to figure out what the formula is, just conceptually is the distance to being doubly balanced. Okay? And the scaling problem now is this tuple of matrices A defining T, they have an approximately doubly balanced scaling if I can find these matrices left and right such that this operator given by L epsilon AI R epsilon, they're very close to doubly balanced in this distance. Okay? So, and then again, we can ask, given this tuple of matrices, does it have an approximately doubly balanced scaling? And if so, can we find it efficiently? And again, always the question that should be in the back of your mind is, how is this related to algebraic complexity theory? Right? That's all we're giving here. So, okay. So let me tell you, Gurvitz just defined this generalization and also generalized the algorithm that I showed to you for matrix balancing, right? And what is the algorithm? Well, repeat k times. You only need to fix the condition that Ti is equal to identity and T star of I is equal to the identity, right? So if, take my operator T, if Ti is not equal to the identity, simply scale on the left to make the Ti equal to the identity. And then you may have messed up the dual, and now you write normalize. Multiply on the right all of the matrices to get T star of I equal to identity, okay? If at any point you get really close to doubly balanced, okay, then you output the scaling. Otherwise, you don't output any scaling. You output that there's no scaling. Okay? And again, the same questions that should be in the back of your mind is which case should we choose, and is there an epsilon naught again, that if I scale to epsilon naught, then I can get as, I know that I'll be able to get as close as I want from doubly balanced. And again, how does this relate to any of these problems that we talked about? Okay, so right now I just threw at you like a lot of optimization. Stay with me because some algebra is coming now. Okay, so at last we can rest. Okay, so how do we analyze this? So the analysis is basic, is very general, and is only based in 3 steps. Okay, and involves invariant theory. So first, we define a potential function to say, well, this is going to converge if some potential function, you know, cannot decrease infinitely. Okay, and what is this potential function? Is the norm of my input. So remember, in my operator, in my matrix scaling, I either was driving my matrix to 0, or my matrix was being driven to like a doubly stochastic matrix, right? So then, let's look at this norm of the input. So if I believe that either I can drive something to 0 or stay really far from 0, right? Then this norm should tell me something. So we know that first, this norm, this potential function, the norm of my input, the norm of my initial matrix, right, is upper bounded by the input size, right? So if I have an integer matrix, you know, you have a good upper bound. So that's fine. Now, we have to say that if we are epsilon far from being doubly balanced, then this normalization, this multiplying the rows or the columns, will decrease the value of the norm by some constant value. Okay. It will decrease by a multiplicatively constant value. Okay? And in the end, we need a lower bound. We need to say that, like, if I can get very close to doubly balanced, then my norm never gets below a certain value. Okay? And the value can be exponential over poly n. Okay? This only means that it's bounded away from 0. Right? And if I don't have a doubly balanced scaling, I'll be able to drive it as close to 0 as I want. Okay? So this is the analysis of the algorithm. Okay? So this approach, you can see that it proves correctness in the running time, in time polynomial n, the bit complexity of your input, and 1 over epsilon, right? Because I start, let's say, my norm is 1. Suppose that my norm is 1. At every time, if I'm really far from doubly balanced, my norm decreases by some constant. Right, like let's say by a half. And I know that my norm cannot be less than 1 over 2 to the n. So after n steps, I must stop. Yeah? Is that clear how this plan works? Okay, so let's see how this works for matrix scaling, and let's see how invariants come into the picture, right? So, okay, so if we look at it for matrix scaling, the potential function is my norm of my matrix, and then okay, I'm not going to show this to you, but this is really easy. This is just AMGM. So if we're epsilon far from the doubly balanced, then my scaling decreases the value of my norm by this constant, okay? And if A now is not in the null cone, remember, the matrix balancing problem can be seen as a following invariant theory problem. I have STN, so these are all diagonal matrices. 1, and Kit defined in the previous talk, STN, and it acts on the spaces of matrices, right? Like these are n by n matrices over the complex, right? And I take my matrix A, I multiply on the left by x1 up to xn, and on the right by y1 up to yn, right? And what is the null cone problem? The null cone problem is, given A, are there sequences of functions that drive matrix to 0, right? But now, we're not doing this. We're doing this doubly stochastic example, right? So what this doubly balanced scaling has to do with the null cone, right? So here, as we saw in our algorithm, if we're not in the null cone, so if I cannot drive it away to 0, I can drive to something doubly stochastic. And here, what we're showing is that if A, my matrix A is not in the null cone, we know that there is a nice invariant polynomial such that the polynomial evaluated at A is different from 0, right? So now, if my polynomial is invariant under this group action, this STN cross STN, then the value of the polynomial PA is equal to the value of the polynomial PB for any B, the scaling of A, right? Because of the invariant property. Now, you know, if this polynomial, what is nice? Let's say that it has integer coefficients, right? Like, then, if it has integer coefficients, my matrix was integer, my PA being different from 0 means that this norm is bigger than 1, which means that for any scaling of A, my norm, the norm of PB squared is also greater than or equal to 1, which means that the norm of B is bounded by this 1 over exponential. Okay? So far, so good? Okay. So, okay, so again, this proves correctness in running time. Okay, but what are these invariants? Let's see what are these invariants that we have. So, in the matrix scaling, Ankit showed in his previous lecture, right, that the invariants here, what are they? They're the matching monomials, right? So, if my matrix A has a matching, okay, let's look at this, let's look at what happens with the matching once I have the action by the matrix X, A, Y, right? So I have B is equal to X, A, Y. Let's look at a matching monomial, okay? So sigma is a permutation. So let's see what happens to product of BI sigma I. So here, BI sigma I is what? XI times AI sigma I times Y of sigma I. But now, if I pull out the X's and the Y's, because this sigma is a permutation, this is the same as the product of the XI's times the product of YI's times the product of my matching monomial at A. But this, remember, this is 1, because the determinant of those two matrices is 1, right? So clearly, these matching monomials, as Ankit showed in the previous lecture, right, they're invariants. And how do I use them for my analysis? Well, now, if A is not in the null cone, then we know that one of these invariants must not vanish, right? So PA is different from 0 for some matching. So I can use this matching to certify that I'm never going to 0. Right? Okay, so then we have that. And so then for any scaling of A, right, like the norm of B is greater than or equal to 1. But what is the norm of B here? Right? The norm of B is essentially the product of the monomials in the matching, which is less than or equal than the norm of B, complete norm of B to the 2 to the n. So we know that, you know, if my matrix is integer and it has a matching, no scaling can make this matrix have norm less than 1. So either my matrix will always have norm bigger than 1, or I'll be able to drive it all the way to 0 if my matrix is in the null cone, right? So that solves the null cone problem, right? If I'm not in the null cone, my matrix will always have norm bigger than 1, If I'm in the null cone, at some point I will get norm close to 1. Yeah? Is that clear? Yeah, so sorry, GA bar means the orbit closure. Yeah, so G is my group and acting on my vector, and this is the orbit. Ankit represented this as O of A, right? So this is a different representation, yeah. So, okay, very good. So let's just run through the analysis again just to, because it's going to get just a little bit notationally hard later. So what is the analysis? So take my matrix A with integer entries bounded by some nu and my parameter epsilon, right? So this analysis, which was done in by Lineal, Samorodinsky, and Wigderson, with a different invariant, but it doesn't matter much now. So at first, my norm squared, it's an integer matrix, right? So every entry is less than nu, so my norm is nu squared times n squared. This is a bound on the input norm. So we have an upper bound on my input. Now, remember, if I'm far from doubly balanced, I know that this normalization will decrease this norm by a multiplicative exponential factor, yeah? So I'm putting the row norms to all be like 1 over n, right? The L2 norms to be all 1 over n. Yeah. And we can prove that this decreases is not super deep. It's some, AMGM inequality, okay? And then we proved by the previous slide, remember that if my A is integer, right, and it has a matching, then, my norm of B, of any scaling of A, is always greater or equal to 1, right? So at some point, if I keep decreasing my norm, either I must get below 1, in which case, this must fail at some point, right? So this is how we use invariant theory to solve this problem. This is how this algorithm, this scaling problem, solves the null cone problem for the diagonal action, okay? So far, so good? Okay, now let's generalize this proof to show how we can solve the operator scaling problem using invariant theory. So, okay. So now, the operator scaling, so I have now, remember, I have invertible matrices determinant 1 that I multiply on the left and on the right. So here, what are the invariants? Ankit showed the invariants like in the last lecture, so I'm just going to show them again. So my invariants are given by these polynomials, determinant of sum of bi, tensor, some other matrices, like d by d matrices yi. Now let's see what happens to this polynomial under scaling, right? So if b is the scaling of a, let's see what happens to the invariant when I evaluate it at b, and the invariant when I evaluate it at a. So this determinant of sum of bi sigma I is equal to, each bi is equal to L times ai times r, right? So then is equal to sum of L, ai, r, tensor yi. But this is the same, since these matrices, I can pull them out of this expression, and I get, this is equivalent to determinant of sum of ai tensor yi times determinant of L to the d, determinant of r to the d, right? It's a simple calculation. But now these guys, remember, their determinants are 1. This means that the invariant this polynomial doesn't change, right? So it's an invariant under this group action. Okay, so we found the invariants. And it turns out that these invariants, they also generate any other invariant, okay, for this action. So then we know that if my tuple is not in the null cone, there must be some invariant of this form for which PA must not vanish, okay? And we need to use this now for the analysis. Now, if my matrix A, my tuple of matrices A have integer coefficients, my yi's, these guys here, I can choose this polynomial to have integer coefficients. Again, if my P of A is different from 0, my norm of P of A is bigger than 1. Right? So this invariant, if it doesn't vanish, it's still really large. The value of the invariant is really large. And again, we can follow the same template. For any b in the orbit closure, the value of P of B is bigger than 1. Right? And this will imply that the norm of B, again, should not be small. So again, essentially, what is the point of this slide? You don't need to even think of this calculation, but essentially, what we are showing is, if you have your group action, and you have nice invariants that define your null cone, right? Like, if you're not in the null cone, and you're an integer point, your orbit, your entire orbit is really far from 0, right? So that's the point of this slide. It's saying that these nice invariants tell you that if your orbit is not 0, it's really far from 0. right? And then, how do we analyze this algorithm?
What do you mean by nice invariant? The polynomials are low degree?
So nice invariants, no, it just means that they have low integer coefficients. Okay, the degree can be large, but the coefficients of your polynomial are small. Yeah, that's what the nice is. Okay, and how do we analyze this? Again, it's the same. We take the norm of my input, the same thing that we did for matrix scaling, right? Our norm of input is bounded, is small. And then, if I'm far from doubly balanced, I need to show again that my norm will decrease by this constant factor, right? And again, we know that if I'm not in the null cone, my norm is really big. I'm really far from 0, right? So then, this means that, I cannot be, like, after I keep normalizing, I cannot, like, be really far from doubly balanced all the time, right? So somehow, there is something about this doubly balanced that allows you to make progress in the null cone problem, right? If you're far from doubly balanced, you can keep decreasing your norm all the time, okay? So then, this also solves the null cone problem for the operator scaling problem, right? Because if I cannot, right, just by trying to get this doubly balanced matrix, we showed now that you're doubly balanced if and only if you're not in the null cone, right? So we solved the null cone problem here, yeah?
You had the Hall blockers or what sort of characterize the null cone.
Yes.
Did you mention already here, or is there an easy characterization? What is the null cone?
Yes. So Srikanth's question was in that action, right, of the diagonal the matrix scaling action, we showed that the Hall blocker was this characterization of things that are in the null cone. And is there an analogous characterization here? Yes. And like Ankit said in his talk to you as well, that said like, well, even in the non-commutative, like there is a similar thing about support, but you need to take care of these rotations, right? Because the non-commutativeness comes from these rotations. So the condition would be that, for all these AIs, okay, there is a change of basis of all of these AIs, such that all of these AIs have a big Hall blocker, all of them. Okay, so it's a generalization of that condition. Okay. So, okay, now, it's kind of mysterious, right? Because in a sense, it seems kind of like an accident that you're trying to solve this doubly balanced problem, and somehow you end up solving this null cone problem because of this like AMGM step happening here, right? But, I mean, what is the meaning of this quantity here, this doubly balanced quantity, that allows you to keep making progress on the norm all the time? Right? Like, what's the conceptual, why is this solving the null cone problem? At some point, these people who are trying to solve this problem, they're not interested, they probably didn't even know about the null cone. But why is this related to the null cone? So let's try to investigate what is this doubly balanced, okay? And to that, let me just give a recap of Ankit's talk. It's been happening, you forgot. So if I give you a vector space V and a group G acting linearly on it, Ankit defined this null cone. The null cone of this action, okay, is the set of all points such that 0 is in their orbit closure, right? And as Ankit said, by a work of Hilbert, given a vector space, given this V and a group acting on it, it turns out that this null cone is the common 0 of all the invariant polynomials, right? So if your point V is in the null cone, it means that P of V is equal to 0 for all the invariant polynomials P, right? And the null cone problem is I give you a point V, right, and it's V in the null cone. Okay, so there's two approaches, right? So one approach is I have this optimization approach. I can minimize the norm of any element in my orbit, which is sort of what we did in matrix balancing, operator balancing, right? Or you can use the algebraic approach. Well, I can just pick all the invariants, and then I can decide if they all vanish, right? But somehow I have to encode all the invariants at the same in an algebraic circuit, and then it becomes a PIT question, right? This is something that Mumu laid, right? So, okay. Now, again, why are we talking about this? Like, show me the doubly balanced. Where does it show up in this invariant theory business, right? Okay, so as Ankit mentioned, there's this work by Kempf-Ness, and as he mentioned, there's this non-commutative duality which generalizes this linear programming duality, right, for non-commutative actions. So we have this problem, which I will call capacity. The capacity of V is the minimum element, the minimum norm of an element in its orbit, okay, in its orbit closure. Now, how do we know Like if I give you an element of the orbit of V, how do we know that we're close to the element of minimum norm? Right? Like if you remember your calculus, you'd say, well, just look at the gradient and see if the norm of the gradient is 0, right? Like the gradient is close to 0. Now, where do we take the gradient? Well, Ankit alluded to it as well. Well, you have to take the gradient along the group action, which he computed, which is erased now, but it had to do with the Lie algebra action around that point, right? And this has, and saying that something is close to 0, I am close to a global minimum. If you remember your calculus days, right? This is a statement about convexity, right? Only convex functions have this really cool property, right? So somehow this is a statement about convexity in this weird space. And we're going to talk about it in a little bit. I have 15 minutes, which should be a lot. That's enough. Okay. Now, again, from Ankit's talk, the work of Kempf-Ness has this non-commutative duality. So he defined this moment map to U, right, which is the gradient along the group action from Ankit's talk. And we have now this dual optimization problem that, like, I can define this mu capacity, this moment capacity, which is what is the minimum norm of the moment map along my group, along my orbit, right? And this work by Kempf-Ness, as Ankit stated in his talk, is essentially saying that, this dual program is bigger than 0 if and only if I am in the null cone. Okay, so that's from Ankit's talk. So essentially, but now, what is the doubly balanced condition? Well, it turns out that doubly balanced in the matrix scaling and the operator scaling, they're both the norms of the moment map for the matrix and operator scaling problem. Okay? This is the highlight of this thing. Because remember, when Ankit computed the moment map for this action, right? And remember, when Ankit computed the moment map for this action, it was something like rho I, it was this vector rho I minus alpha, all ones vector, right? And then you have column J minus the all ones vector, right? Like same alpha, right? And if you remember, this is exactly the condition that we have for being close to doubly balanced, right? So from Ankit's talk, you can see that these guys, these doubly balanced, they are the norms of the moment map. So all we were doing, we were saying, well, as long as this value is really big, we make progress in this optimization problem, right? So there's this primal dual approach to solve this problem, right? So this, in a sense, is the dual program to this problem, okay, in the non-commutative world, okay? So essentially, what does this mu capacity bigger than 0 mean? Like if I'm far from doubly balanced, it means that I'm in the null cone, because I can keep driving my norm to 0, yeah? Okay, so let's just look again at the same algorithm to indoctrinate ourselves that this is happening, right? Like, so if I just look at this line here, was the line that I was trying to understand, right? Remember, my doubly balanced is bigger than epsilon, is bigger than some constant, then my norm decreases by a lot. Well, this part means that I'm far from a solution to the dual, right? My capacity is big, and this means that we make a lot of progress in the primal, right? So I have dual, and then I'm in essentially the approach. Okay, work. Now that I showed to you how this has a lot to do with invariant theory, even this doubly balanced scale is an invariant theoretic question, right? It's just the dual program of the null cone. Let's talk a little bit about orbit closure intersection, okay? So again, just a recap from Ankit's talk. Again, if I have this left-right action, so my group is SLN cross SLN, my vector space is this tuple of matrices, I have this left-right multiplication. Again, my orbit closure is take all elements of the group and act on it, and then take the closure, the Euclidean closure of the set, right? So the orbit closure intersection problem now is, if I give two tuples of matrices A and B, do the orbit closures intersect, right? We know that if V is equal to 0, for example, this problem becomes the null cone problem. And from Ankit's talk, we saw that this has connections to non-commutative PIT, non-commutative algebra, combinatorics, and so on. It's really amazing already, the null cone problem. But let's try to solve this more general problem. Okay? How can we solve this orbit intersection problem for the left-right action? Right? So what do we need to do? Well, it turns out that this operator scaling, this operator balancing that we had, this algorithm, is not enough. Okay? And why not enough? Well, it was enough for the null cone problem, but it could, remember, the operator balancing works because I told you, if my orbit doesn't have 0, then it's really far from 0, right? But here now, I can have two orbit closures that they don't intersect, but they get very close to each other. They get exponentially close to each other, okay? And remember, our algorithm depended on this epsilon being big, this gap being big. So now the gap is really small. So, you know, we need to have this epsilon now 1 over exponential. That's pretty bad. So we cannot use that, you know, vanilla operator scaling approach, which is not the case for the null cone problem, right? So, and again, the operator balancing runs in times poly n 1 over epsilon, so this is pretty bad. Okay, so then operator balancing is only good for null cone. So what do we need to do now? Well, we need log 1 over epsilon convergence. We need an algorithm that will give you this log 1 over epsilon, right? And for that, we need a different algorithm, okay? Now, what is going to be our approach? Well, remember, if you remember the algebraic approach, you could have said, well, let's just solve a PIT problem. Because how could I test null cone algebraically? Algebraically, you could say, look at all the invariants and find an invariant for me that is different from 0. The orbit closure now could be, and as a result, okay, you have to prove this, but it's a result by Mumford, that like, if two orbit closures don't intersect, there is an invariant that evaluates differently, in different values. So you could do a PIT there as well. But, you know, that's a bit hard. Let's try to solve it by optimization again. So let's explore this duality theory by Kempf-Ness again. So what do they say? Well, they say that elements of minimum norm are these doubly balanced operators, right? So epsilon close to doubly balanced implies that I'm epsilon close to minimum norm. That's what we saw in the null cone slides, right? But now, what this Kempf-Ness says as well is that, as Ankit mentioned in his talk, that if two elements, you know, in my orbit closure are of minimum norm, it must be that there is a rotation that takes one of them to the other. So essentially, all the elements of minimum norms, they're rotations of one another, right? So there's this unitary transformation that takes A, B to C, okay? So in a sense, modulo these rotations, there is a unique minimum. This is the kind of non-commutative convexity that you have. So, and now, what was our strategy? How do we solve this orbit closure intersection problem analytically? Well, one, we use some convex optimization, okay, that I put G there. I'll explain what the G is, to find this epsilon approximation to the element of minimum norm with really good precision. My epsilon can be exponential. I'll find this really fast. And once I have an element of minimum norm from one orbit and an element of minimum norm from another orbit, I just need to test if they're equivalent under rotations. Okay, so this is a completely different algorithm, but this is the second part, right? You find two elements of minimum norm, one of each orbit, and now your problem is to test if they're equivalent under unitaries. Because if they are, your orbits are the same. If they're not, the orbits must be different. Does that make sense? So I'm not going to focus on this. Let's just focus on how to get the element of minimum norm really fast, right? Which is a speed up on our null cone algorithm. Okay? Now, what is this G convexity that I was explaining to you, right? So let's talk, before talking about G convexity, let's talk about regular convexity. We're in Euclidean geometry. What is convexity? Well, shortest path between 2 points is given by the straight line between them, right? Now, what is a convex set? A convex set is a set such that for every 2 points, I take the line between them is in the set as well, right? And what is a convex function? Convex function is, okay, I take any line, and then I take the value of x and the value of y. This line between x and y is above the values of my function, right? So here, this function will be convex, right? Now, if I have a convex function over a convex body, I know that I have all these beautiful algorithms, and there's a lot of theory to solve these problems really efficiently, right? Okay, now what is geodesic convexity? Geodesic convexity is the following. Now, the shortest path between A and B is not given necessarily by straight line, it's given by this geodesic, okay? And for example, if you look at Earth, right, you cannot go through tunnels. So if you go from P to Q, right, you have to go through the meridian here, through the diagonal, like, path, right? So this would be the geodesics on Earth, right? And what is a geodesically convex set? Well, it means that if I pick 2 points, the geodesics between them, they are in the set, okay? And what is a geodesically convex function? Is, again, if I restrict my function to be univariate in every geodesic, this function is convex in the sense that I described in the previous slide, Okay? This is the generalization. Okay, you can see here some pretty picture of geodesics, right? If you have the sun, then, light is gonna, space is curved, so it's not Euclidean. So, but now, even though this is cool and this exists in the universe, like little is known algorithmically about these guys. We don't have these awesome ellipsoid algorithms or so on. Right? So we need to develop this new optimization algorithms for these geodesically convex problems. So in our setup now, what are the geodesics? Well, first, we're going to solve a problem over this complex positive definite matrices. So all symmetric, like all Hermitian matrices, positive eigenvalues, okay? And what are the geodesics here? Well, the geodesics between two matrices, A and B, is given by this ugly expression here. All you need to know is that when t is 0, I'm at A, and as I move along t, I go t is equal to 1, I get to B. Okay, so just trust me that this is. Okay, now convexity is, again, if for all A and B, this geodesic from A to B is in my body, right? And my functions is G convex if when I restrict my function from this convex body, geodesically convex body, to any geodesic, look, I get a univariate function. It's a function of t. So this function is regularly convex, okay, in t, for any points in my convex body. Okay? Now, what are geodesically convex functions? Why are we talking about this? We're trying to minimize norm or minimizing moment map. Well, but guess what? It turns out that these functions, the log of the norm of my vector, okay, and the log of this positive definite matrix here, these two functions, they're geodesically convex over the space of positive definite matrices. So how lucky are we, right? Not that lucky, because other people already knew about this. So, like implicitly, they knew, right? But we're really lucky, right? So it turns out then, but this is geodesically linear, so it turns out that this function here is geodesically convex. So now all we need to do, is to just make a new algorithm for it. So let's make it work, right? So, but we don't have ellipsoid, we don't have interior point methods, okay? But we can get inspired by these interior point methods, right? So in interior point methods, you have this concept that is really marvelous. It's called self-concordance, okay? So it turns out that if a function is self-concordant, if, the third derivative, okay, it lower bounds the second order derivative to the 3/2. Okay, so here, notice that this is a norm, so this function is definitely convex, right? But there is this factor here, this 3/2 to normalize. So this means that the function looks like a convex function in a global sense. Okay, like looks really convex. This function is definitely convex because the second derivative is bigger than 0, but it looks really convex everywhere. Okay? So it doesn't look like something really ugly that's kind of hard to optimize, right? Like something like this is really hard to optimize, right? But like something like this, we know it's easier to optimize. That guy looks very, very convex. That's a definition of, if you want to think of something very convex, it's a self-concordant function, okay? But unfortunately, log of capacity is not self-concordant, okay? Or geodesically self-concordant, whatever you want to know. But there's this concept of self-robustness. We can say, well, requiring these 3/2 here may be a killer, right? What if I don't require that 3/2? Now notice that, these guys are, well, this is the degree 3 polynomial, this is the degree 2, so it's a scaling, it depends on scaling now, right? But, it's self-robust if it's self-robust along each line, okay? But we have this condition which is a bit weaker than self-concordance, okay? Now, lucky for us, this log of capacity that I defined to you is geodesically self-robust, okay? So, and what is the difference between, ignore these ugly lines. So what is the difference between self-robustness and self-concordance? Self-concordance looks kind of globally very, very convex, whatever definition of very convex. This guy, self-robustness, locally, in every small neighborhood, it looks convex. Which means that now, in self-concordance, you can take really big steps when you do, your interior point methods. But here, with the self-robust, it's very just locally convex. So you can only take small steps. Okay? So that's the difference between these two concepts. Okay, and now the question is, okay, log of capacity is geodesically self-robust. Can I optimize these self-robust functions? Okay, and the answer is yes. And how do we do it? Okay, so that's the problem. The problem is to optimize this function f over a geodesically convex body. And what we show is that there exists a deterministic algorithm, which is polynomial in n, the size of the input, r, and what is r now? R is the distance that you are from the minimum element of the orbit. Okay, so if I'm r far, then this r enters here, and log 1 over epsilon for optimizing these G self-robust functions. Okay, so if I'm really far from my element of minimum norm, this algorithm is really bad. But if I'm really close, then we get the log 1 over epsilon that we wanted. Okay? So, and this, just so you know, it's a second order method. It generalized some work that we had before in 2017, and Madhava et al. Had for matrix scaling. Okay? And generalizes to other manifolds, not just this positive semi-definite, positive definite matrices. Okay? Now, for operator scaling, if I put f here to be the capacity, right? If I find this x epsilon such that my capacity of x epsilon is less than or equal to the minimum norm plus epsilon, it means I'm very close to the element of minimum norm. So that's what I want, right? I want to find this I want to develop this algorithm because I want to find this scaling that's very close to doubly balanced, right? Okay, so here's the algorithm. Okay, so start with your scaling being the trivial scaling. So if I had the matrix scaling, for example, I would start with identity here and identity here. Okay, and I'll repeat this for my L number of steps. Okay, so now what I do is, if I'm at this point, I'm at this point, so x is my scaling, okay? So here in the matrix scaling, I don't need to have x and y. I can have always y as a function of x. So I can always work with only one matrix, okay? So if I start the matrix with x being identity, it turns out I will be identity. But then, how do I update my scaling? How do I go from x, from identity to the next scaling step, right? So what I do here is, we have this function at the tth level, which is the function at my scaling at time t, and now I have my scaling I'm going to try to find the scaling for time t plus 1, right? And now what I do is, I have my log of capacity. I take my quadratic approximation to the log of capacity. Because remember, because I'm self-robust, it means that, 1 minute, okay. So because I'm self-robust, it means that in a small neighborhood, I look a lot like a quadratic function. So I take the approximation of the capacity to a quadratic function. I minimize, I find the minimizer of this quadratic function, okay? And it turns out this minimizer is a good approximation of the minimizer of f in this small neighborhood. So I make locally small progress. But remember, I'm only taking steps of size 1. Because remember, my function is locally like a quadratic function, right? It's not globally, it's not like the self-concordant. So, okay, and I keep updating. Okay, so this is the usual second order method, okay? Now, why would we need this instead of the regular scaling? Again, it's because we need exponential precision, right? Now, you have to ask, well, what is this bound R for operator scaling? If I start at a good point, how far am I from doubly stochastic? Then we have to show that, there's a polynomial bound for this R. So the scaling, I'm never too far from the scaling. I'm always polynomially far away from the optimum scaling, okay? Okay, so then again, why do we need this log 1 over epsilon convergence? Is because we have to get exponential approximation. And to solve this orbit closure intersection problem, I showed to you how we can find this element of minimum norm, and then we're only left with checking if two things are rotational equivalent, right? If these two elements of minimum norm are rotational equivalent, which we can test, okay? So, okay, some advertisement. There's an amazing workshop in 2018, which, together with this amazing workshop, we have lots of videos on operator scaling. And Ankit did not mention the survey that we wrote on ICTS. So thanks, Arvind, for inviting us to write this. And some open questions now. So now I showed to you how to solve the orbit closure intersection problem in the operator scaling problem. But as Ankit mentioned, there's lots of group actions out there that are waiting to be solved, right? So can we, so what is the complexity of even the null cone problem for more general group actions? And of, orbit closure intersection. As he was saying, we don't even know if these things are in NP intersection co-NP, right? And other open questions is, can we get better algorithms for more general scaling problems? Right now, the best algorithms we have are polynomial in R times log 1 over epsilon, and we got lucky that this R is polynomial for the cases that we're interested in, right? But can we get better algorithms? Yeah, and again, solving these null cone problems and orbit closure intersection for more general actions, right? So that's all.